Okay, so here's problem 2.39. This one I think is a little complicated just from getting the description. Putting the picture together might have been tricky for you. So let's go through that first. Um, Looking at my picture, I did it a couple ways. So first I did just what I tried to make was a diagram to show here early on, let's say at 0 meters, at some initial origin, um, here's where the cup has been sitting. That's my bike cup. And so then the car comes by, and so when the car crosses the 0 meter mark, it's already going 83 kilometers per hour. And at this point, the cup is going 0 kilometers per hour. It's stopped. And I'm considering this my initial time, basically. And then at the end of this situation that's being described in this problem, my final time, if you will, my cup has now gotten up to speed, but logically you know that the car's still going to be ahead because this guy hasn't been going 83. This guy has been going 83. He's had to catch up. So he's still behind when he gets up to 83. So that's why I'm drawing him back here. So then to show you on a graph what that looks like, I've got my car that's driving, going at their constant speed of 83. So the slope here would be up 83 kilometers and over 1 hour. So that would be the slope here to show that that's its velocity. Now the cup is going to be speeding up, and then when these are parallel, right about here, that's when they would be going the same speed. And then maybe eventually the cup would speed up some more so that it could actually catch the car. Here, just looking at their velocities, we start out with the car going 83, and the cup starts out going at 1, so the cup's going to have a constant acceleration while the car is going at a constant velocity. And eventually they're going to get to that point here where they're going the same speed. So this point in time here matches this point in time where it looks like these have the same slope, where these are about parallel to each other. Okay, so this is where we've got the same speed over here. This is where we've got the same speed over here. Perhaps the cup continues driving and gets a little bit faster so that he can get to a point where he catches up to the car so he can pull him over. So that's what could happen, but that's not what the question is asking about. The question is asking about this time when they're going the same speed, when the cup gets up to 83 kilometers per hour. It's right here. Okay, now then, knowns and unknowns. I listed my knowns for the car and my knowns for the cup. The car going at a constant velocity, I'm just going to be listing velocity, change in time, and change in position. I went ahead and converted 83 kilometers per hour to meters per second. You guys should know how to do that. I expect that you guys will show me that you've done that on your assignment. And then for the cup is accelerating, so we're going to do VV-tex. 0 kilometers per hour is also 0 meters per second, so that doesn't matter. The final velocity of the cup has to be the 83, which is 23.1 meters per second. The time, I don't know. The acceleration for the cup they gave me was 8.5 meters per second squared, and the change in position, I don't know. One thing to point out here is that the amount of time it takes for the cup to speed up is the same amount of time that this car has been driving at a constant speed. So I'm using the same time here and here. In order to find this change in position, you've got to figure that speed out. But I can't figure that out because I've only got one variable over here and I'd need two. On this side, remember that when you're using VV-tex, when you've got constant acceleration, if you know 3 of these, you can solve for the other 2. So I've got 3 variables over here, so I can solve for time and then bring that time over here. And I believe part A wants you to find time anyway. And then part B wants you to figure out the actual distance between the two, the cop car, or the cop on the bike, and the car, your car, when the cop actually gets up to speed. So you're going to have to find the difference between those 2 distances in order to figure that out. Okay, so let's go ahead and start out with that time. How would we calculate that time? Well, using our note cards here, if I want to find time and I don't have a change in position, then I'm going to want to stick up here to the, I'm so sorry. Then I'm going to want to stick up to either equation 1 or 2. Since this has the change in velocity already combined, I'm going to go ahead and just use this. And honestly, at this point, we should be pretty comfortable with the fact that if acceleration equals change in velocity over change in time, then change in time is equal to change in velocity over acceleration. So that really shouldn't be a stretch at this point. You guys should be able to see that that's what's going to happen. So for my change in velocity, well, 23.1 minus 0 is going to be 23.1 meters per second. My acceleration is 8.5 meters per second squared. Go ahead and plug that in. And we get 2.7. So about 2.71, 2.72 seconds. So that's going to be the time. And that time will be used in both of these pieces. Here's 2.72 seconds, 2.72 seconds. Now, where part A asks you for that time, you do need to put the correct number of sig figs, which, based on the 83, we know is going to be 2. So make sure that you round it off to the correct number of sig figs. But here, I don't think this rounding is going to make much of a difference in our actual number. It's when you round off again and again and again in problems that take multiple steps, and if you're rounding off by a lot, then you kind of want to keep those. This to being 2.7, that I don't really think it's going to matter anyway, so we could probably just use 2.7 in the next part. So what we need to do next is figure out what our change in position is for the car and for the cop. So let's go ahead and take care of the car first. So for the car, we've got, this is constant velocity. So we know that velocity is equal to our change in position over change in time. I'm trying to solve for change in position here. So I need to rewrite this as change in position is equal to velocity times my change in time. Oops, excuse me. Let's just write it like that. I know it's sloppy, I'm sorry. So that's equal to then my 23.1 meters per second times that time that I just calculated, 2.7 seconds. And I get 62.37 meters. I'm not going to round this off yet because I still have to do that subtraction bit from this part here, figure out where the cop is, because I'm looking for the distance between them, not just how far each of them is going. Okay, so then next I need to figure out that change in position for the cop. So got to go back to my constant acceleration equations. We can use any of these. We can use any of these that actually has change in position. These first two don't. So either 3 or 4 is fine. Let's go ahead and use 3. We haven't used 3 yet. So let's use 3. Delta x is equal to, let me move this so that you can actually see what I'm writing. Chill out. Whew. Delta x is I was saying chill out to the computer, not you guys, just so you know. 1/2 times acceleration times my change squared plus my initial velocity times time. Remember, according to this, the cop's initial velocity was 0. So here, if this is 0, anything times 0 is going to be 0. So I'm just going to stick a line through that already. And I like to write a little 0 there to remind myself. I cross this out because this is going to be 0. And now I can plug in the rest of the information I know. Delta x is equal to 1/2 times my acceleration. That was the 8.5 meters per second squared. And then times my time squared, so that's going to be the 2.7 seconds. That's going to be squared. Let's see what we get. Okay, might as well keep this number in here, because that was my time. I'm going to go ahead and square this number, and then times 8.5 and times 0.5, I get 31.39. All right. So now I need to subtract this number from this number. So, if I just do subtract 62.37, then, I get a negative number, but I know that that's positive. So my change in position then, or the distance between them, so delta x of the car minus delta x cop is going to give me that 30.98, which, rounding off to 2 sig figs, is going to be 31 meters. Yay! Good, good. And that's it.